Okay, welcome to my talk. My talk is about simulating quantum qubit correlations with classical communication. And the main question is we take some very basic or very simple quantum devices. So for example, entangled qubit correlations, and ask, can we simulate the same correlations with a classical protocol? So instead of actually performing using quantum devices, are the same correlations also obtainable in a classical setting? And in the first part of my talk, I will focus on quantum communication, and in the second one on the task of simulating quantum entanglement. So more precisely, I will stick to the following setting, which is a prepare-and-measure scenario, and I guess it's familiar to most of you. So more precisely, we have Alice and Bob. It's a bipartite setting, and they are allowed to send a qubit to each other. So Alice can prepare the qubit in any state she wants, and Bob can take the received qubit and apply any measurement that he wants on the qubit, and then he produces an outcome that follows the laws of quantum mechanics, so Born's rule. So, what is interesting about this scenario? It's the most primitive scenario we can think of for a quantum communication task. So, as a warm-up, let's do a little task. So, what we are asking in quantum communication is often we have a task and we ask how well can we perform with certain resources. So, for example, can we perform the task with 1 bit or 2 bit or a quantum message? So, in that example, we have Alice and Bob, and Alice receives, for instance, from an external referee 2 bits, and these 2 bits are either 0 or 1. And the referee asks Bob, can you tell me the first bit of Alice? Or respectively, can you tell me the second bit of Alice? And the task is performed if Bob outputs the correct answer. So now we can ask how well can we do in this task with certain resources? And if you think about it, if Alice is allowed 2 classical bits, she just sends these 2 bits, and Bob knows the answer. He just decides which one he wants to read out. On the other hand, if they are allowed to send just 1 bit, Alice has to make a decision, for example, to send the first one, and then, in the case that Bob is asked to read out the first one, they win, but otherwise he has to guess and they cannot perform it perfectly. So why am I showing that? Because it's the simplest task that provides a quantum advantage. So more precisely, if they can now send the qubit, they have a winning probability of 85%. And this is important because it's, in my opinion, one of the most basic tasks that provide an information theoretic advantage of using quantum correlations or qubit correlations in that case. So why is it so? We have a clever quantum strategy that is very useful in this task. So given her input, Alice is not sending a classical message that she prepares a qubit in a certain state, sends that to Bob, and he can read that out in a qubit out in a certain basis, depending on which bit he wants to read out. And it turns out if they perform that protocol, they are very successful and they win with probability of 85%. So this is interesting because it shows that we have at least some situation where it's more powerful to send 1 qubit compared to 1 classical bit. And then it's natural to ask, can we do, since we have an advantage of 1 qubit compared to 1 bit, is it also possible to find another task, where we have, for example, an advantage of 1 qubit compared to 2 bits, or even 3 or 4, or even more? And in general, we can consider any task that we want. So Alice has an arbitrary input, Bob as well, and Bob in the end is asked to output a certain function of these inputs. And the main message of my talk I can already show you on that slide, and that is you will never find a task where 1 qubit is better than 2 bits. And why is that so? Because it turns out that 2 bits of classical communication are always sufficient to simulate all correlations you can achieve in a qubit scenario. So more precisely, we are asking the following question, Alice can choose an arbitrary state she wants, and Bob can perform an arbitrary quantum measurement on the received qubit. Is there a protocol that can simulate all of these strategies. So for every state V and every state measurement that I have here, like just to notice, like all my drawings are in 2 dimensions, but in the end they represent like 3-dimensional objects, like qubit in the Bloch sphere. And the question is, like, is there like a classical protocol that achieves the same correlations? And if we can do that, it means that like we can apply the same strategy with these classical resources and achieve the same like winning probability, whatever the task is. And this question was already asked like 20 years ago. And the most like notable work here is the one of Toner and Bacon. And they show indeed that all correlations we can achieve here can be perfectly simulated by by sending just 2 bits from Alice to Bob, as long as Bob is restricted to projective measurements only. However, and this is now our contribution to this task, like there's no reason why we should restrict the measurements on Bob's side to be only projective. Like we have more general measurements in quantum theory, and these are like POVMs. And they are even known to be very powerful in many like information theoretic tasks. So there's no reason why we should exclude them. And what we found is that even if we consider these more general measurements, like 2 bits are sufficient to like simulate all of these correlations and perform the task we are interested in. So let me first try to argue why this question is actually not trivial. And this, or one thing that is always possible, let's say, what is a naive approach to this task of like simulating quantum correlations? Like one thing that is always possible, Alice just sends like the coordinates or like a classical description of the state she wants to send to Bob. And this is always sufficient for Bob to produce an outcome because he knows exactly which state Alice wants to send. And then he just uses Born's rule and calculates his outcome. But as you might see, this is a continuous parameter that Alice needs to send in this case. And if you want to do that, this requires an infinite amount of classical communication. So this works, but it's not very efficient. And indeed, like 20 years ago, like clever people came up with a much more efficient protocol that can be used to like simulate everything that can be achieved in a qubit communication scenario. And like I decided to show you the explicit protocol. This is due to Toner and Bacon. And the reason why I show you is because like I found it like very simple and it's not, in my opinion, not super hard to understand. So how does it look like? So it turns out that for these protocols, like we always need some shared randomness. And what it means is basically, so Alice and Bob, they meet at some point before they actually like separate, and they agree on some shared random vectors. So more precisely, they choose 2 random directions in the Bloch sphere and label these like vectors as 1, 2, 3, 4. And these vectors, so they just know it, and then like they can separate from each other and start the actual communication protocol. And how does that look like? So Alice, she can choose the state that she would like to send in the qubit scenario. And now they don't have like quantum resources, they have a classical protocol here. So what she is doing is she checks which of these 4 vectors they agreed beforehand is the closest one to the state she wants to send. So in that case, it would be lambda 4. And she exactly tells Bob to use only that vector lambda 4 and forget about all the other ones. And since there are 4 vectors beforehand, like this requires 2 bits of communication because we have to discriminate between 4 different elements. And now Bob is informed of that vector. He knows which one to use. And he can choose the measurements that he would like to perform on the qubits I want to simulate, and checks if the vector that he got informed of, in that case lambda 4, is closer to this minus or to this plus part of this projective measurement. And then like he just outputs whether it's closer to plus or minus. In that case, it would be a -1. And it turns out, and this actually is a surprising thing, that if say Alice and Bob follow this protocol, then like the probability that Bob outputs plus or minus 1 in the end follows exactly Born's rule. So it's exactly what we need, what we have in the quantum protocol if they actually would send a qubit state from Alice to Bob, and Bob actually performs that measurement. And like this looks pretty deterministic, so where's the randomness, like, but quantum mechanics has probabilistic outcomes, so where's the probabilities come from? And they come indeed from this randomness that they share in the beginning. So more precisely, so just in this particular situation, she picks lambda 4, and then he outputs minus 1. But if these vectors would be distributed differently in the beginning, then maybe she would pick a vector that is here, and that would be closer to plus 1. And it turns out that on average, like Bob exactly outputs plus and minus 1 with the correct probabilities. And I find this protocol, to be honest, very elegant. So it inspired me a lot, and it's also like the reason why I decided to work on that. So what is also interesting here is that like if Alice decides which message she sends, she does not have to know anything about what Bob is going to measure. So we can really assume that like Alice does not have to know what Bob is measuring, and Bob does not have to know what Alice is measuring. So Alice learns a bit, Bob learns a bit about the states that Alice actually wants to send him, but not enough to exactly determine which state it is. So more precisely, what he knows in the end is that it's closer, like the states that Alice wants to send is closer to lambda 4 than to the other vectors, but that's it. So like he learned something, but not sufficient, but still it is surprising that like it is indeed enough to come up with an output for Bob that satisfies the same like rules as like a quantum protocol. All right, so one thing that is always so a bit more about the intuition. Like what is the idea of the protocol, or how do you come up with that? Like the idea here is somehow like Alice sends not enough information for Bob to know the state. Like we learned that this would require an infinite amount, but she sends exactly enough information for him to come up with a correct output that satisfies the correct statistics. And like if we look at the distribution of the vector lambda that Alice picks, then it's very likely to be close to the actual state that like Alice wants to send, so close to the state V. Simply because of the like characteristics of the protocol. If there's a vector very close to V, she is very likely to pick it. And then also sometimes it happens that it's a bit further away from V. And this distribution is known as a Cauchy-Specker like hidden variable model of the qubit. So it's a way, basically, I will say a bit more about it in a second. It's a hidden variable description of the qubit, and it's like basically not enough for Bob to know the state, but enough to produce an output. That's somehow the secret of this protocol. But as I already mentioned, there's one drawback, and the drawback is that there are more measurements in quantum theory than just projective measurements. And these are POVMs. And now the question is, like, how does the situation changes if we do not only consider like projective ones, but general POVMs? And like we found an explicit protocol that also simulates these things with just 2 bits of communication. So what's the idea here? Like, in a nutshell, the idea of the old like protocol of Toner and Bacon is like Alice tries to prepare for Bob from these shared random vectors that they had in the beginning, a distribution that looks like that. So like the vector lambda that she picks in the end is close to V, but also not exactly. And this distribution is enough for Bob to come up with an output that satisfies the correct statistics. So indeed, he checks, like he takes his measurement and checks if it's closer to plus or to minus. And in principle, he can do it for every measurement direction, and that will always lead to the same or to the correct statistics that satisfies the laws of quantum mechanics. And the drawback is that like this model works only for projective measurements. So what we had to come up with is we had to come up with another model that is also possible to like give us the correct statistics for other measurements. And we found one. And now, like instead of like having just one vector according to a certain distribution, we have a hidden variable model of the qubit that has like two vectors, and they also have a certain distribution, namely they are like equally distributed in the hemisphere that is spanned by V. So basically all of these vectors in a distribution have a positive like scalar product with the vector V that this ensemble is supposed to represent. But yeah, outside it's 0. And like the idea of the new protocol basically is for Alice, she tries again to like produce such a distribution to Bob, because she knows that like for a given POVM and whatever POVM that might be, like Bob has like a recipe to come from these like two vectors up with a result that obeys exactly quantum statistics. And the protocol then follows immediately from that. So they again start with some shared random vectors. And now like Alice tries to like sample such a distribution to Bob. So she can again choose which date she would like to send, and checks like if these two vectors that they had are already in the correct hemisphere or not. And if not, she tells Bob to flip that vector. And in that case, like lambda 1 is already correct, so it's closer to V than to minus V. It's in the correct hemisphere here. But lambda 2 is not, so she has to tell Bob to flip that one. And that requires like 2 bits, one for lambda 1, one for lambda 2. And then it's not hard to see that the distribution at the end is exactly the model that we need. And from that, he has a recipe, like he knows what to do to find like one of the outputs for these POVM elements that obey exactly quantum statistics. So this part is a bit harder to explain, so I decided to skip it. So, but if you believe me that this is possible, then the protocol basically follows. And this like can be used to simulate like any qubit PM, like prepare and measure scenario with just 2 bits of communication. And that's, I think, in my opinion, like the main message. And to come back to this task that I had in the beginning, let's suppose you have a given task, whatever it is, and then you come up with a very clever quantum strategy to do, like to solve the task. And now instead of like actually sending a qubit, like you go to this protocol and you have the same correlations, so you also have the same winning probability. And that shows that like 2 bits are always at least as good as the qubits in whatever task you have in this communication scheme. All right, so in the second half, which is just like the last 2 minutes, I have to talk about like simulating quantum entanglement. And basically the question that we ask here is very similar, just the setting is the same. So again, we have Alice and Bob, and they share like an entangled qubit pair in the simplest case. So like Alice can perform an arbitrary measurement on her share, and Bob can perform an arbitrary measurement on his share on the pair. And we have some correlations. And now what we know is that like all qubit pairs, they violate a Bell inequality. So what it means is that like they cannot reproduce the same correlations with just shared randomness. But then you can ask, okay, if they cannot do it with only shared randomness, can they do it if they like in addition like communicate a little bit of information? And if yes, how much information is that? And it turns out that this is surprisingly little, even when we consider like general measurements on both sides, and Alice does not have to know anything about Bob's measurement, and Bob does not have to know anything about Alice's measurements. They can choose completely freely. So just a brief sketch. What is the idea here? Basically, we can use the protocol that we found before and use it like to simulate, we can apply it to this task of simulating quantum entanglement. So let's suppose you are Alice, and you perform a measurement on your share of the qubit pair. And so you know which measurement you would like to apply, and given your outcome, like the qubit state of Bob collapses to you, right? So you know the post-measurement state of Bob's qubit. So what you can do is you just use the qubit channel simulation that we had before to send like a classical description of that qubit to Bob, and this is all he needs to that's all he needs to know about his qubit. And it's reasonably simple to convince yourself that this indeed shows that in this protocol they have the correct statistics, and altogether it shows that 2 bits are sufficient to simulate local POVMs on any entangled qubit pair. However, it turns out that often we can do better. And so now I will just briefly sketch what's the idea here. So more precisely, 20 years ago, Toner and Bacon showed, if we restrict to projective measurements, and Alice and Bob share a singlet state, so a maximally entangled state, there is a protocol that just communicates 1 bit of communication. But for all other states, non-maximally entangled, it requires 2 bits. And that was a bit funny. So why do we need more resources to simulate the states that is less entangled? And it was open for since 2003, can we also simulate these other states with 1 bit or with less than 2 bits? And we found a way to do it. And just very briefly, the old approach is basically we need 4 vectors, and so with the approach before, there are 2 post-measurement states of Bob, and with a certain probability Alice prepares 1, and with this other probability Alice prepares the other post-measurement state. And what we found is that it's more efficient to simulate both post-measurement states together, and that also can be used to simulate the same statistics. And what this leads to is that we managed to simulate projective measurements on any qubit pair with one classical message of 1 trit. So 1 trit is a message where you can send 3 symbols. And if the state is very weakly entangled, then even a single bit is sufficient. And if the entanglement goes to 0 here, where p equals 1, then it turns out that the bit is not even necessary in each round. So it's only necessary sometimes, so the communication cost goes really to 0 as well. All right, so with that I would like to finish. I apologize for the 3 minutes overlay. And here are some open questions. Basically what I want to say, beyond the qubit case, basically nothing is known. For example, let's replace a qubit with a q trit. Then we don't know if there's any finite simulation. And there are a lot of open questions. So thanks a lot.
Thank you, Martin.
Yep.
Yes, thanks a lot for the nice talk. So here you are considering the task of, so in the end, for instance, of simulating a Bell experiment with communication. But you can also look at a second question in which you consider a noisy state, a noisy maximally entangled state, a Werner state, for instance, and you try to simulate any potential Bell experiment to find a local model without communication. And very often these models have the same flavor. So does what you did can help to improve, for instance, so the Werner model or the Barrett model, which can simulate some noisy states?
Yeah, that's a very good point. Indeed, so we have not checked too much, but one thing that is, for example, open is if you have a Werner state, like a singlet, a noisy singlet with visibility 1/2, and you apply local POVMs to both sides. Then we don't know if this state is local or non-local, right, I guess. And in principle, so let's suppose we find a 1-bit model for the singlet and POVMs on both sides. Then this would imply such a model. We don't have that yet, but what we have is a special case, where one side applies projective measurements and the other POVMs, and this turns out to be sufficient with 1 bit. So I think there are a lot of nice like questions in that direction, but we don't know yet. Yeah, thanks. It's a very good point.
Yeah. Thanks for a nice talk. My question is, what do these results, what is the implication of these results on QKD and secure communication protocols?
So can you repeat again?
The implications of your results on secure quantum communication protocols, or do they work in the asymptotic regime when probability is to be simulated, the statistics system simulated?
So applications to QKD.
Yeah.
So to be honest, I don't know much about QKD, so I cannot answer. But yeah, I don't know. I don't know. To be honest, I cannot give you a good answer because I don't know enough. But I think there are other people in the audience who might know more about that question. Sorry.
Thanks for the interesting talk. I wanted to know if you have thought about some explanations for your results, thinking about state spaces of like the 1-bit and 2-bit simplices versus the block sphere, and is there any way to see your results in this kind of a picture?
So what was the block sphere versus?
Versus the simplices, 4 bits, the state space for the bit, or 2 bits, yeah.
So what it implies, yeah, so if you have the state space like that corresponds to 2 bits, which is a simplex, right? That means, so if you have a GPT with that state space, and then you consider all the correlations you can obtain there in this prepare-and-measure scenario, it turns out that this can simulate all qubit correlations. Yeah. So, okay, one thing that I should maybe mention, like it turns out that these 2 bits in the protocol can be replaced by 1 G-bit. So a G-bit is the element of box word. It's basically 2 bits, but you are allowed to read out only one of them. And it turns out this is sufficient. And I think this is interesting from a GPT perspective. So that means all the correlations you can achieve with a qubit can be simulated with a G-bit. I think that's interesting. Maybe, yeah, that answer, or that gives like something for you.
Okay, so maybe the last question.
Yeah, just a follow-up question, basically to your answer just now. What I don't quite understand is that what you're doing here is, okay, we have some pre-shared randomness, and then on top of that, we restrict ourselves and we only have to communicate this much classical information to simulate the correlations or the measurement outcomes of a qubit or an EPR pair. But if you're saying like, okay, then I only need to share this very restrictive amount of classical information, or I should just put out like a G-bit. I wasn't familiar with it, but aren't you kind of grossing over the fact that you already have this pre-shared randomness? Because in an EPR, for instance, in an EPR experiment, the whole point is to generate this shared randomness by means of an EPR pair, for instance. And now you're saying, okay, if I already have this, then I can simulate generating this. And of course, you can simulate more, but isn't it a quite heavy? Maybe my point is, the question is, isn't it a very heavy constraint that you already have this pre-shared randomness?
A very good point. So, so what I'm implicitly assuming is that shared randomness is bit for free. Like kind of for free, right? And it kind of makes sense because like if Alice and Bob are together, they can like share randomness, and this is like rather simple to do, let's say. And then if they separate, they can like consume the shared randomness. You can ask the same question, can they perform this task without shared randomness? And then it turns out they cannot. They need like an infinite classical message. That's a nice work by Serge Massart and others from like the 2000s. That's very interesting.